Hey guys, I'm going over the answers for the magnetism review. The test is Monday test. Okay. I kind of have the slideshow just so you can see where I'm at. So if you just have a specific number you're looking for, then you can fast forward and know where it's at. All right, number one, what did Hans Christian discover as a result of his experiments? He discovered that when he turned an electric current on, that his compass moved. And so he made the correlation that electric currents cause magnetic fields, or that they're tied together. Okay, that's what you need to know about the man. Number two, I want you to describe the following. The first thing I want you to describe is the first right-hand rule. All right, so with the first right-hand rule, you're going to point your right thumb along the flow of the current, and you're going to wrap your hand around a wire. The direction that your fingers point is the direction, or point is the field. So imagine like the coils wrapped around the wire or wrapped around a magnet. Okay, so your hands are like kind of like the coils. So there's no coils here because it's one wire. And you're wrapping your hand around the wire. This is how the magnetic field goes. Your thumb is out. Okay, so your fingers are like the point of the arrow. So this field is going in this direction. Okay, that's the first right-hand rule. For the second right-hand rule, you're going to curl your fingers in the direction of the current, and your thumb will point in the direction of the North Pole. So now you have the coils wrapped around here. You figure out which way the current's going. You wrap your fingers that way, and the way that your thumb points is the direction that the North Pole is. Okay. The third right-hand rule, you're going to point your fingers in the direction of the magnetic field. Okay, so say it's pointing towards you. All right, your thumb is in the direction of the current. I'm just going to make this up, that the current's going straight up. Okay, and the palm will face in the direction of the force acting on the wire. All right, I got all three of these descriptions from your notes from Monday, so go back to those notes if you need to. The notes on Monday also tell you 3A, B, and C. Okay, the first right-hand rule tells you the direction of magnetic field around a wire. The second right-hand rule tells you the direction of the magnetic field in an electromagnet. And the third right-hand rule tells you the direction of electromagnetic force. Okay. Number four, when looking at a magnetic field on paper, arrows represent the direction the force is traveling, but how do we represent if a force is going into the page? All right, this would be from the assignment from Tuesday. It wanted you to mark an X if it's going into the page, and it wanted you to mark a dot if it was coming out of the page. So X is when the force is going into the page, a dot is when the force is coming out. We're dealing with 3D things, so that's why we have to use different symbols. Okay, so sorry, 4A is the X, 4B is a dot. Number five, explain why bar magnets cannot be separated into individual north and south poles. They break into, when you break one apart, it's breaking into another north and south pole. So that's like if I take a piece of paper and I rip it in half, okay, it's still like, so let me change that up. So this is the north end, this is the south end. When I rip it in half, the half sheet, okay, this is still the north end, and now I have a new south end, okay? And then with the other magnet, I now have a new north end and the same old south end. So as you break them apart, it's still the same. It still has a north and a south, and it doesn't separate them. Number six, what is the difference between the magnetic domain in a non-magnetized versus magnetized materials? Okay, so if a material is not magnetized, that means the atoms are not aligned. So all the electrons and everything are pointing in different directions. When they all line up and face the same direction, that's when you have magnetic material. That's what happens with iron, okay? Let's see. And then this leads to number 7. Does the magnet strength always remain the same? Why or why not? No, magnets don't always have the same strength. That's because the atoms can change their directions. So like if you have a magnet and you drop it, it's going to lose some power because the atoms are going to rearrange themselves from the shock. But then if you take a strong magnet or if you, like Mr. Graham showed in the video yesterday, okay, you can recharge the magnets and that aligns everything back up. So magnetic strength can change. All right, number 8. Is the current in a wire directly proportional or inversely proportional to its magnetic field? It's a direct relationship. Direct relationship, remember that as one increases, the other increases. So the same thing happens to both. If the current gets stronger, the magnet also gets stronger. Number 9, if a wire were running from left to right on this page, and the current was also traveling from left to right, the magnetic field in the top half of the page would be traveling in which direction? Okay, so I'm gonna have to try to do this from your perspective. So we're looking at the camera. Okay, let's see. So left to right. Okay, and the current's also traveling from left to right. Okay, so the current's traveling left to right. I wrap my hand, my fingers are telling me which way it's going, and it's wanting to know about the top half of the page. Okay, so in the top half of the page, my fingers are pointing out. Okay, so it should be out of the page. Number 10 says, if a wire were running from left to right on this page and the electrons was also traveling from left to right, the magnetic field on the top half of the page would be traveling in which direction? Remember, electrons travel opposite of the current. Okay, so if the electrons are traveling from left to right, that means my current must be going from right to left. All right, and for the top half of the page, now which way is my knuckles facing? Towards the page, so that means it's going into the page. What right-hand rule is that? Number 1. 11, where does Earth's magnetic field come from? It comes from the core, okay, the middle part of the Earth. It's rotating and it has iron material in it, and so that's what causes the magnetic poles. All right. Number 12, how do you induce a current in a coil of wire? By moving it in a magnetic field or by changing the magnetic field around it. Okay, getting the particles moving. That's how you induce the current. Let's see. Number 13, what conversion takes place in a generator? Okay, so the generator is, think of like a wind turbine. The wind makes the windmill move. Okay, that gets movements in the generator, and then turns that into electrical energy. Okay, so it's going from mechanical energy with the movement of the generator into electrical energy, and then the conversion that takes place in a motor. Right, so that's going a motor's going from electrical energy to mechanical energy. So the electrical energy is making something move. All right, that was number 14. Sorry, I jumped ahead. Okay, so if you need number 14, rewind just a little bit. Number 15, what is a solenoid and what is it used for? It's a coil of wire that's used as an electromagnet. Okay, so whenever we have all the wires coiled up, that's the solenoid. I could be saying it wrong. I say things wrong all the time. Okay, number 16, define the following. Do that on your own, okay? You can Google define answers if you need to. All right, and number 17 says there's nothing to answer here, but make sure you're familiar with drawing magnetic fields for magnets that are attracted to or repelled by each other. All right, look over your notes, look over your worksheets, and you guys are gonna rock this test. All right, have a great weekend. Remember, the test is Monday.